So, this is the second session of the morning, and I'm pleased to introduce Professor Radoslav Harman from Comenius University discussing construction of efficient experimental designs under resource constraints.
Thank you. So first of all, let me thank the organizers for inviting me to this most wonderful place again. Today I decided to talk about something less technical than usual, perhaps mathematical, not so beautiful, but I hope useful, at least potentially useful. This is a talk, this is a joint work with my younger colleagues, two girls, Alena Bachrata and Lenka Filova from Comenius University in Bratislava, and Guillaume Sagnol from Zuse Institute in Berlin. Okay, so after a brief introduction of the basic terminology, I'll talk about the most important notion of this talk, its resource constraints. Then I talk about what we mean by exact optimum designs under these resource constraints. So I'll focus on exact optimal designs, not the approximate as before. And then I talk a little bit about a taboo search heuristic that we somehow engineered to solve the associated problems. And as the most important example of this talk, prepared especially for this conference, I computed some optimal designs for dose escalation trials under resource constraints. And then I'll talk a little bit about another approach, mixed integer second order cone programming, and say something about conclusions. The talk is mostly based on these two papers, mostly on the first paper. All of them, both of them have already been accepted, and they are also available at arXiv. Okay, so as usual, an experiment is a set of trials. By a trial, I mean some elementary act of obtaining an observation, either real valued or multiple valued. It doesn't matter. For each trial, we must select a design point from a finite design space X. So another point to note is that the design space here is just finite, okay? But it can be large. This represents permissible experimental conditions. And an exact experimental design here is a mapping from X to non-negative integer numbers, okay? With the interpretation that psi X determines the numbers of trials in the design point X. We will also use a little bit an approximate, sometimes called continuous experimental design. And here, this is not normalized. It's not as usual. We assume it just to be a relaxation of an exact design as defined before. But in some instances, it's not the proper thing to do to consider normalized designs, especially in cases like this, when we do not know in advance what will be the number of trials. It is most usual in experimental design that we set in advance what will be the required number of trials. Not here. So I cannot normalize it somehow. The number of trials will be sometimes will be one of the outputs of the optimization procedure. Then I'll consider a very general optimality criterion. Optimality criterion maps this capital I to the set of non-negative real numbers, and it measures a quality of information content of these designs for statistical inference. Here, note that again, this information criterion is not defined, this criterion is not defined on the set of information matrices, but rather directly on the set of designs. Most of the effort, of the most useful effort in optimum design of experiments goes to determining what this should be, because this criterion essentially contains also the model, not only the d-optimality or optimality or anything. We just consider it very general, in a very general form, some function that assigns some value, non-negative value, to the designs. In a sense that the higher the value of the criterion, the better the design. Okay, so we are talking about maximizing the information content, not minimizing some kind of loss. We will have only one assumption, which is very natural, an assumption of monotonicity. Augmentation of an experiment by additional trials cannot decrease its quality for statistical inference. Okay, so if we simply have one experiment and add some trials to this experiment, we cannot decrease the measure given by this criterion 5. It must be more information in this experiment. So that's all that we need to assume for the algorithm to work. Of course, as such, this problem would be not well posed, because the more trials we perform, the higher informational content. We must have some limits. The usual limits are the limits on the size of the experiment. Simply, we say how many trials should be in the design. But let us look at more complicated constraints. It is a very interesting and useful area of research under studying optimum designs under linear or even non-linear constraints. The most basic paper to read in this respect is a paper by Professor Federer and Professor Cook, which appeared in 1995 in the journal Statistics. But if we consider the most general system of linear constraints, it turns out that a set of feasible exact designs, again, I'm not talking about approximate, but exact designs, can be very complex. It turns out that it is not so simple to prove that there is an exact design, at least one exact design under general linear constraints. Okay, so just merely proving that there is a single exact design that conforms to some general system of linear constraints may be a difficult problem. Okay. So what we suggested in that paper, and what I suggest to consider, whether perhaps it should be enough, is the class of so-called resource constraints. Okay, so resource constraints are some general constraints. This is the form, a schematic form of these resource constraints. We have some coefficients here and some coefficients at the right-hand side. The interpretation is that these ARX represent consumption of the rth resource. So we have k resources. This denotes 1 ... k, so the set of all natural numbers from 1 to k. So ARX represents the consumption of the rth resource by an observation in x. And BR is a limit on the rth resource. Okay, so we consume some resource with each trial. And if we according to this interpretation, these limits must be non-negative, of course, but also these consumption coefficients must be non-negative. Okay? And there is a third very natural assumption that no trial is completely free. In no design point, the trial is completely free. And its replication eventually results in exceeding some resource limit, which means that for all x, there is some resource such that the corresponding consumption coefficient is strictly greater than 0. Some special cases. So what we can cover by these constraints, which cases? So first, the most standard case, the size constraints. It is very simple to formulate within the framework of resource constraints the same resource coefficients, and the limit is n. Cost constraints. Okay, again, it is simple. If we have possibly unequal costs of trials in the individual design points, it's simple to capture them as resource constraints. But also direct constraints. Okay, so we can have that we cannot perform more than a given number of trials in some design point, usually just one trial in a given design point, and it can be captured by direct constraints that are special case of the resource constraints. Strata constraints. Let us talk perhaps about time separation constraints. Okay, that can be captured. If the experimental domain is represents a time points, then using this special case of resource constraints, we can tell the experiment not to concentrate points too close to each other. Just they need to keep between two successive experiments, between two successive trials, we need to have at least a given amount of time. Okay, so all these kinds of constraints, even some kinds of Latin hypercube constraints, if X is a cubic grid of points, and so on, many constraints can be captured by resource constraints, although not all linear constraints. Okay, so we also need for the algorithm to have some design to be augmented, some primary design to be augmented. And then the set of exact feasible designs is non-empty, finite. That's the result that follows from the definition of resource constraints. They are much simpler. And simple to explore using heuristic optimization methods. That's most important for the computational part. Using optimization method based on transition between neighboring feasible design points. If we had general linear constraints, then unfortunately we might have some islands of exact designs such that we cannot transform from one exact design to another exact design without violating some of the constraints if we just add one or delete one design point. Okay? This is not the case for resource constraints. So it's a particular nice class of constraints for heuristic methods. And also the class of feasible approximate designs is very simple. And it's convex, compact, and polyhedron. This is a scheme of how it looks like in a very simple case when we have just two design points. Okay, so this x is just 1, 2. Okay, and these red points denote the feasible exact design. This area is feasible approximate design, and these blue dots are infeasible exact design. So these dots are designs. Okay, because sometimes it leads to some confusion. These are not the design points. Those are not design points. These dots are designs. Okay, so perhaps this design, very simple. This design perform one trial in the design point 1 and one trial in the design point 2. Okay. So the main optimization problem is like this: simply maximize the value of the criteria of the monotonic criteria of the set of exact designs. It turns out that as I formulated it in this general framework, it's very, very general. Okay, it contains many combinatorial optimization problems, very hard, NP-hard combinatorial optimization problem like knapsack problems or optimal redundancy allocation and reliability theory, to give something more specific, some problems in graph theory, and so on, very hard problems. So in general, the classes for computation of such methods are enumeration methods, where we can find perfect solution, but usually only for small problems, and heuristic methods, where we obtain possibly non-optimal, suboptimal solutions of large problems. And it is not completely trivial to devise an efficient enumeration method. Of course, a brute force enumeration may be simple to program, but there are much more efficient enumeration methods based, for example, on branch and bound. Okay? So we will talk a little bit about, we'll describe the taboo search heuristic method, and then we will briefly talk about the mathematical programming method that can be used to tackle this problem. Okay, another terminology. An exact design is called maximal if it cannot be augmented without violation of some of the resource constraints. And monotonicity of phi implies that the set of maximal design contains at least one optimal design. Okay? So we can essentially, we could only focus on the maximal designs, but the structure of the set of maximal designs is rather difficult. Okay? We must somehow move between these maximal points in a logical or in an efficient way using sub-maximal design. Okay? We need, for this design, for the algorithm to work, we need first a local heuristic evaluation of each design. So it means what is the quality. It roughly estimates how promising xi is as a part of an excursion leading to an efficient design. Okay, that's somehow a general statement. In the actual implementation, we devised, again, we engineered after a couple of trials and improvements. We engineered one way how to heuristically evaluate these designs. And what is perhaps a little bit surprising is that this evaluation depends also on some approximate designs. Okay, so not only on the values of the criterion in these exact designs, but also on values of approximate design, because the local evaluation is a functional value, criteria value of a extremal approximate design that augments xi. Okay. Also, the residual amounts of resources come into this evaluation, but I do not want to be technical. I just didn't put the formulas here. And we also need a characteristic attribute of the design xi, which we need to devise it such that it assigns different values to substantially different designs and the same values to essentially same designs. Okay? Most importantly, in problems with many invariances, okay, and invariant problems, it is very good approach, because then we skip somehow enumerating or going through the same so design that are essentially same, that is isomorphic, for instance. Okay? And what is the essence of the taboo heuristics is that we keep some taboo list in which we store the attributes. And we somehow, using this taboo, we somehow avoid the designs that we already visited. Okay? We look at the taboo in the taboo list, and then if some designs in the neighborhood of the current design are in the taboo list, we try to avoid them. Okay, I will not go into details because I see the time is running, so I will not go into details of this algorithm. It is perhaps more appropriate to check it if you want to see details in this paper form. Okay. Perhaps better is to give you some very simple picture. If we start with this initial design, then the algorithm moves. Okay, there is a criterion phi. I didn't know how to plot it here. Simply criterion phi generally increases in this direction. Okay, so we move in a greedy way to obtain some maximal design. But, well, this would be a local optimum. A standard heuristic would simply stop in this point. But this heuristic, it doesn't get discouraged. It simply somehow, using these rules, avoids these designs and follows a path to the optimal design in this case. Okay. So, by the way, these yellow dots are maximal designs. We see that it's difficult to know the set of maximal designs, even in this very simple case and very simple picture. I'll specify it. Okay. So we have some heuristic. We tested this heuristic on many examples, with block models with limits on the numbers of blocks and replication treatments, regression model with simultaneous marginal, constant direct constraints, many. To give you some impression, some idea about the speed, it usually takes less than 300,000 criterion evaluation to obtain a nearly optimal design for a problem with up to 100 design points. It turns out that the number of design points, which would be the number of dimensions of this picture, okay, is the most limiting factor. Okay, so if it's 100 or 200, it's still fine. So, for instance, for block models, we were able, with 16 treatments, we were able to find a design which is better than the design with a strongly regular concurrence graph. Okay, for those of you who know, I will not go into the details. There is a conjecture that designs with strongly regular concurrence graphs might be de-optimal. So this is not true. For 16 treatments, and 48, for instance, 48 blocks, there is a design which is better than the strongly regular design in this setting. For this n, there is a strongly regular design, and we found somewhat better design. The strongly regular design is very efficient, 99% or something. But there is some kind of not yet unexplored beauty to these de-optimal designs. For instance, this is not this means this is not the complete concurrence graph. It would be too messy with 48 edges. All these edges mean bipartite graphs. Okay, so every of these edges is a bipartite graph, even here and also here. Okay, sometimes it turns out that the optimal de-optimal designs with block sizes 2 contain very many bipartite graphs. Okay, always, even in these cases. Okay. So let's go to a-optimal designs for dose-founding studies, which is the main example. We have a placebo and n doses. That is, the number of treatments is n+1. The treatments are applied to individuals in T cohorts. That is, we consider the so-called extended dose escalation designs, not the standard ones. We have therefore a block design with cohorts corresponding to blocks. We can use this following model where the tau i's are the effects of the treatments and the k's are the nuisance effects of the cohorts. And what this dose escalation means is it's used in the first main studies, but of course I will shorten this as much as possible because we will have a real expert talking about those escalation studies in 10 minutes. Okay, so very briefly, the main requirement of this dose escalation is that for cohort K, no individual allocated dose is K plus 1 to very high doses K plus 1 and so on. We also require that in cohort K at least one individual is allocated dose K. So the basic reference, at least for me, is this Bailey in Statistics in Medicine, and I also used Linda's paper from 2014 in Statistics and Computing. Essentially, I replicated some of these computations. Okay, so here the design space is like this. Essentially, this part is the extra cohort. Okay, and the interpretation of design Ki is that Xi Ki gives the number of individuals of the kth cohort allocated to the ith treatment. Okay, and there is an additional constraint that we need to have at least one individual in the escalation dose, which can be captured by this design Xi node, which is to be augmented. So what are the resource constraints in this case? For example, overall number of individuals can be limited. Sizes of individual cohorts can be limited from above. Replication numbers of treatments, cost of the entire experiment can be limited, and so on. So let us look at some concrete values and concrete designs. Oh, and before we need to specify what the criterion of optimality is in this case. We will use criterion of A optimality, and which is simply, this is the usual information matrix for this parameter of tau effects, effects of the treatments. Of course, this is singular. We cannot estimate these treatments all, just some contrast. And the criterion of A optimality is an harmonic mean of the eigenvalues of this information matrix of all except of the smallest one, of the 0. Okay, so this is the example calculated by our algorithm, but it's completely the same as in the Haynes paper. So this is our benchmark paper. You see the requirement here is to have in each cohort to have exactly 8 individuals. Okay? But what if there is no requirement on the number of individuals in each cohort? Just the total number of individuals. Okay, 40. I know that is perhaps not the best thing to do, okay, but let us try. Perhaps Rosemary knows why this is not the best thing to do. But here what happens? This is the optimal design immediately calculated within a small fraction of a second by our algorithm. Okay, it gives the same numbers of replications, which is nice for these kind of models, of course, but it gives very unequal cohort sizes. Okay. However, statistically speaking, it is more efficient than the previous our benchmark design, 123%. But somehow it comes and says, all right, the cohort of size 19, it's too big. We cannot do with 19 people in one day, say. Well, I asked people who know more about this, and we can manage at most 11 people in one cohort. No problem. Within 5 minutes, indeed, I did it within 5 minutes. In fact, I consulted with my wife, and she asked me to do that and this, and I also always, in 5 minutes, produced the results. Okay? Okay, so this is another 5-minute result. Okay, cohort sizes are limited. Cohort sizes are limited by 11 from above. Of course, we also have the number of individuals limited. It's 40. Okay, here we already see 6 resource constraints, simultaneous resource constraints. And this is the design that is, again, a little bit more efficient than the benchmark design. Okay, replications are still rather similar. But then another comes and, well, here, this is a very small cohort. I need to have at least 2 people on placebo and 3 people on the escalation dose. No problem, we can do this with our algorithm. So we increase the 2 here and to 3, at least to 3. And this is perhaps a little bit boring design, but this is the A optimal design within these constraints. Okay, and the relative efficiency is still higher than the standard Haynes-Clark design, say. Okay. Fine. But then there is another guy who is even more concerned about the safety. Okay, and he tells us not to just to escalate the dose, but to escalate the number of individuals per each dose. So for example, here we must have at most 1, at most 2, at most 3, at most 4, at most 5 people at this dose. This is a very cautious design, I would say. Okay. No problem with this. We have 20 resource constraints, simultaneous resource constraints, but the algorithm works very fine. Within approximately 1 second, it produced this design, which is now a little bit less statistically efficient than the Haynes-Clark design, but still rather good. Okay. Okay, I see that my time is almost up, so I will not go into this mixed integer second order programming approach. I will leave this for my talks in London and Sydney in December. Of you who are I will talk about this mathematical program method in a very mathematical talk. Okay, this was not that mathematical. Okay, so I will leave this. I will also leave this comparison of heuristic methods and integer programming methods. And go directly to the conclusions. So summary. Optimization under multiple constraints can be used to construct statistically efficient experimental design that conform to, and now I collected all the words that I heard in this conference. Financial, material, logistic, operational, or safety requirements, okay, perhaps. The problems of optimal exact designs under multiple constraints are computationally very challenging, but today we already have efficient heuristic and mathematical programming algorithms that can provide optimal or near-optimal solution for at least some, I'm not claiming that all, realistic situations. So thank you for your attention.
If not,